Hello. It's my pleasure to welcome you to my talk with the title From Prototype to Operation Software with Rapidminer. I'm going to talk about the data analytics processes at Lufthansa, and mainly at Lufthansa where I work in the projects at Lufthansa Passage, which is dedicated to bringing passengers actually from point A to point B. So the usual outlook on the agenda. First of all, I was told to put in some marketing slides here. Lufthansa Industry Solutions, who we are, what are our daily challenges that we face. Then I want to talk about one use case in particular, a little bit more in detail, namely flight prediction, where we predict the arrival times of aircrafts in Frankfurt and Munich. And I want to conclude by talking about the partnership of Lufthansa Industry Solutions and Rapidminer. So first of all, who are we? As you might or might not know, the Lufthansa Group consists of many different sub-companies. The biggest one is probably the passenger airlines. Lufthansa Passenger, for example, but also Swiss and Austrian belong to that part of the company. Then we have aviation industry, air freight, and so on. But I work for a digital service company, namely Lufthansa Industry Solutions. We deal with external customers as well as internal customers, and approximately 50% of the revenue from our IT consultancy comes from external customers. So in here you can see that we have worked with many known customers from all over the industry, public transportation, car manufacturers, everything, and also internal customers belonging to the Lufthansa Group, for which we have projects successfully delivered. Yeah. We are based on all around the world, but mainly in Hamburg, Norderstedt. Here are some hard facts about our cool company. We were founded in 1998, make about 200 million euros total revenue a year, have over 1,000 employees and over 200 customers. So now that you know who we are, let's talk about this handsome guy. I was founded in 1985. And I hold a PhD in number theory. You can see some of the past on the left side. In the present, I'm dealing with predictive analytics at the Lufthansa Group, doing the usual stuff like classification, regression, recommender systems, and a little bit of probabilistic modeling. I'm using multiple technical stuff that you can see down here. And in the future, I hope to dedicate myself a little bit more to probabilistic modeling, time series analysis, and Bayesian learning and learning theory, which I find really interesting. What are the daily challenges that we face from day to day? We have a broad variety, and I can only talk about the things that I have seen, while there are probably more technical people around me as well. For example, we have some dashboarding tasks where we try to visualize airplane punctuality, competitor information, and so on. The central part, of course, predictive analytics, where we predict arrival times of passengers that will make or will not make it to their connection. Fuel and weight forecasts is obviously really important for Lufthansa because one can save a lot of money by saving fuel. And there's also some predictive maintenance stuff going on. We have some projects in deep machine learning, mainly recognition. One use case that we have here that I want to mention is where we predict failure of parts of escalators or electric staircases by listening to the sound they produce, which is kind of cool, I think. And then we have some chatbots ready called Mildred for the Lufthansa website. Then we also face some data ingestion tasks, like we want to bring together some live flight data and weather data streams with the historic data that Lufthansa has collected. I don't want to put you through the whole history of data science again. You have seen that quite a lot of times and will see it more times this day. But let me show you how we approach these challenges by showing you our process model, our data cycle that Wikipedia obviously has stolen from us because they look similarly. There are two entry points, either with a business use case hypothesis given to us by the customer. Could be a question, is it true that this and that holds? Can we predict this and that quantity up to a certain performance that we need? But it's also possible that customers approach us, or we approach customers, and they just have some data and they don't really know what to do with it because they are on such an early stage of the digitalization strategy And then we come up with some sensible, hopefully sensible use cases and use case hypothesis that we then try to test and entry into the data cycle as if we had been given these questions initially. This data cycle consists of the laboratory stage, where we try to play around with the data a little bit, and then once we are satisfied, we go into the implementation stage, where we push really that product that we have designed into production. And the key is the goal is to run through this cycle, to go through this cycle as quickly as possible with the quality asserted that we really need. I want to go through this cycle with one use case in particular, namely flight prediction at Lufthansa. In this project, we predict the arrival time of an aircraft, of every aircraft that departs wherever in the world, for example, in New York or Japan, when it will arrive in Frankfurt or Munich or German airports in general. So I want to go through this cycle a little bit more in detail. The business, in this case, we choose this entry point. We were given a use case hypothesis. Can we predict the arrival time of aircrafts well enough, whatever that means? So here's the goal and the process, how such a flight is usually handled. You can see, so the time is moving from the left to the right. At the beginning, the aircraft is at its departure gate, at its departure airport, and rolls off to the runway where it ignites the engines, takes off, does some flight phase in here, descends towards landing, and then rolls again from the runway, from the arrival runway to the arrival gate. And what we want to do is, at the point where the aircraft takes off, at this point in time, all the future is blurry to us, and we want to predict this point in time, the arrival at the destination gate. So this is the goal. One might ask, well, Lufthansa is an air industry company. Aren't there any predictions right now? And in fact, there are predictions. And in here you can see, so this is also a timeline. Time is moving from left to right, and the bars should indicate, it's without any numbers, it's just the principle that's behind it. Bars should indicate some error that the existing predictions make. So they can overshoot or undershoot. Because of that, there's a bar at the top and a bar at the bottom, going down. So there's nothing to really understand. It's just like there's some error, and the error goes down over time. So when we start in here, the error is quite big, and the error goes down and down and down over time, because as the aircraft approaches its landing site, we remove, so some uncertainty about where the aircraft goes and so on is removed, right? So when the aircraft is already 50 kilometers away from Frankfurt or so, then there's no uncertainty about the way that it takes to Frankfurt. What our goal is to make a new prediction at this point in time at takeoff that is better than the existing prediction, and also the error decreases over time. And the goal is to make it so good that it always stays below the error of the existing prediction. So how do we do that? We unleash the power of big data. Lufthansa has, luckily for us, collected some historic data about flights that went off years ago, and has put that into a data warehouse. We take some other data streams or data sources, historized flight data streams, Eurocontroller and weather data. We put it all together and then head over to a modeling server where there's Rapidminer software running, and we build some nice predictive models. And then the live data is fed into the reporting server, which is coincidentally the same as the model building server at the moment, but it's not necessarily the case in general. And this reporting server comes up and cooks together some predicted arrival time using the model that we have computed before. So that's just the usual predictive stuff, right? So now we are at the data acquisition. What is the data that we actually need in order to predict the arrival time? In here you can see some features that we have selected because we thought that they might be helpful. First of all, we predict the flight duration and not the actual point in time where the flight arrives, because this is a timestamp, and timestamps are a complicated data type. They are difficult to predict, while flight duration is just an integer or a numeric number. So automatically we include the delay at the point in time where the aircraft takes off. That is good. We put in some seasonality, some lagged features. What I mean by lagged features, I will talk about that a little bit more in detail later on. We put in some weather features, because when there are storm cells or weather situations on the way, then the aircraft has to go around them, and this causes some delay. We put in information about the route and the distance, about passengers. For example, in here we put in the number of passengers with the connecting flight at the destination airport. The reason for that is that we suspected initially the pilots to know about the number of passengers with the connecting flights, with the close connecting flight being on their aircraft, and so they might go a little bit faster when they know that there is a close call. With if the aircraft is full with important people that have a high loyalty status and you know you're going to be late, then you think about whether you want to go faster or not. The runways is also interesting because, especially for short-haul flights, for example, I have to travel from Hamburg to Frankfurt regularly, and if you start towards the north in Hamburg and you arrive at the wrong direction in Frankfurt, then the whole flight will take 15 minutes, 10 to 15 minutes longer than when you start and arrive at the right direction. So that's why runways are important. Also, the traffic situation is interesting at the destination airport because if the airspace is really crowded, then it might cause some delay when the aircraft tries to land. But some data is still missing. We are not really happy with that situation right now. We're working on it. We need information about special service disruptions. For example, there's not only storm cells or thunderstorm cells that might cause some delay on the way, but also the military is able to block some region, some area in the airspace. And in that situation, the civil aircraft has to go around it as well, which might cause some delay as well. For the route and distance, at this point in time, we only have the information from the so-called flight plan, which is printed roughly 100 minutes before the flight actually departs. So we would need some more actual data. And for the traffic situation, we also need a capacity index because if you have some information like at this moment, within a certain range of time, there are 10 flights allowed to land on this and that runway, is it much or not? We don't know. We need to know how many flights are allowed in total. So, for example, if there's space on the runway for 30 aircrafts to land and we're only using 10 of it, then the traffic situation is quite relaxed. And if 10 is the maximum number of allowed landings due to some weather situation or so at the departure, at the arrival airport, then the traffic situation is quite bad. So now that we have acquired some data, let me skip these data integration and exploration phase because this is more technical nature. I don't want to talk about this too long. What about the model building? In this case, we just have, right now, we just have one model, namely one gradient boosting model with fixed hyperparameters, which already performs well. Not too good, but well enough for now. Some lessons learned is a few rolling window features are good. These are the lagged features that I meant. By lagged features, I mean that I want to put in the past of the target variable. So I can't put in the target variable itself because I want to predict it. And in here, it was a good idea to put in the target variable, the flight duration of the last instance of this flight and the flight before, and then some rolling window over it and some information that puts that together. And by doing that, you intermix somehow like the usual prediction surfing on the wave of now with the time series approach, which turned out to be really good. Also, we prefer models that can be trained fast and we prefer playing around with features instead of complicated models because these are they contribute more to the increase of performance. Again, I'm going to skip the process improvement and the automation. I just want to talk a little bit about the visualization. We have created some dashboards. These are dashboards. I will explain them. The data is made up, so there's no actual error of 40 minutes or something, which would be insane. But just so you get a feeling of how the error looks like. So we have our prediction, the yellow line, and the other prediction that exists already, the blue line. The error of the blue line starts quite up here and then decreases over time. The reason for that is that this blue prediction may renew itself over time. And in here we have put all the flights together in the sense that if they have different actual durations, then we put them and we normalize them in the sense that they go for one time unit or so. So it's like percentage of flight done and how was the error at that particular point in time for that flight. And the interesting thing is that our prediction is just a line because we are not able to renew it at this moment. This is the next step that we are going to take. And the interesting thing is that although we are doing just one prediction at the start, we are better than the existing prediction, and up to 60 or 70% of the flight, our prediction stays better. And then the other prediction becomes better as there's almost all of the uncertainty is removed, as the flight is so close to its departure, to its arrival airport. And the second graph is more or less the same, just the normalization is different. We just check all the flights at a certain amount of minutes before the actual arrival and wanted to see whether there's some strange pattern, and indeed there's. So the pattern in general is the same. We have a high error in the beginning and then it goes down, it drops over time because the uncertainty is removed. But we have this funny bump in here, and if you want to know more about it, I can tell you in detail after the talk, or maybe you can explain it to me. We'll see. So how do we save money with this model? One of the business cases that lies behind it, why the people pay me and pay us to do it, is connecting passengers. So connecting passengers means that the passenger has booked some inbound flight to Frankfurt, for example, say from a German airport, from Hamburg to Frankfurt, but he actually wants to go to New York, so there's another flight that he has to catch in Frankfurt going to New York. And the usual situation is like this. The inbound flight arrives at a certain point in time at gate Z50, let's say it, and the outbound flight leaves at gate Z99, and the passenger needs a certain amount of time in order to move from the arrival gate to the departure gate. And in this case, he or she has enough time, a sufficient amount of time, and goes to his outbound flight, and everybody is happy, right? So this is what we like. In some situations, the inbound flight is delayed, and also the gate may change due to that delay. And in that case, it's the amount of time that the passenger needs in order to go from one gate to the other might be increased as well, caused by the delay. So in that situation, the passenger is really mad at Lufthansa because, he has to wait. He's not able to catch his flight. In the case where the outbound flight, this one here, is a long-distance flight, as it is usually the case because you travel from Hamburg to Frankfurt and then to somewhere in the world. That's the way how Lufthansa is organized. It might happen that this is the only flight, in fact, on that day. So in that case, we have to put this poor guy in here into a hotel and pay him a nice supper and breakfast, which is costly. What can we do against that? Well, had we known in advance that the inbound flight is delayed, we could have activated some countermeasurements. For example, when you go to the airport, you see sometimes small electric cars trying to navigate through the passenger flow. And these electric cars is a countermeasurement that we as an airline can activate. We have to tell the Fraport, the people at the airport in advance that we need this car, and we only have a certain amount of cars every hour, like 8 or something. I don't know the precise number. But had we known in advance, we could have activated the countermeasurement and everybody is happy again, and we would have saved 100-something euros for putting this poor guy into a hotel, right? So then we just came up with this graph. On the x-axis, we just have the date. The data is made up again. It's just about the principle behind it. The yellow bar counts how many people we have saved on that day due to our model, due to the predictions. And the blue line is extremely important. The blue line is the most important thing in this whole project because it tells you the potential benefit, how much could we have saved by using our model. And you make it cumulative so it goes up and up and up. It's always good for the business people. So this lesson learned, one slide before, the operation. When we put it into operation, we have also, so all of this was designed with Rapidminer, and we have also designed a supervisor Rapidminer process that just asserts every hour that there's enough data, there's enough predictions coming out of the model, the predictions are produced fast and so on. So it just verifies that the system is happy. Now, lessons learned. The first lesson learned is that we need the supervisor and this dashboard, and especially this benefits dashboard stating how much we could have saved that transfers the data science stuff that nobody understands into business language, a euro sign, right? How much money would I have saved is something that everybody can understand. We need these things really early, as early as possible, because they help us extremely in making this product that we develop acceptable by the users. Also, we realized that we have some need for standards, and especially when we do many different projects with Rapidminer, we came to the conclusion that we need to develop some skeleton template where people just change the way how the data is pulled from the database, what the actual model learning algorithm is, and some pre-processing steps, and then they are more or less ready to go and turn it into, due to the fact that Rapidminer allows us to turn processes into web apps or web processes, web services quickly, they are pretty much ready to go after that. So that just speeds up the process, and we don't have to do the same steps all over again whenever we start a new project. Yeah, let's conclude by talking about the partnership of Lufthansa Industry Solutions with Rapidminer. We have a strategic partnership that was founded in 2015. Actually, marketing did not want to show this slide because of the heart symbol. They said, no, heart symbols we don't do, but I don't care. We use Rapidminer really widely in the Lufthansa, many different projects concerning prediction of passengers, aircrafts, and everything. It keeps up with the market technologies. We pair it up with tons of different other technologies, and we are really grateful that Rapidminer allows us to put some general boxes R and Python in it. And we, as Lufthansa Industry Solutions, we have some certified Rapidminer trainers in case anyone is interested in learning how to use this software. So we are allowed to offer that. Yeah, that's pretty much it from my side. Thanks for your attention, and enjoy the rest of the day. Yeah, right.
I think you want to feedback also.
The thing is that we, as like the IT company, in the IT subdivision of Lufthansa, we don't have an actual influence on the pilot, how fast it will fly or not. So that's the first thing. But technically, we could have done this and tell the pilot, go faster. But in the moment, this is due to technical reasons, that the communication, there's a small bandwidth for the communication with the pilots. And we are not on it yet. But maybe this would be a good idea to tell the pilots. But I think in general he knows that he's going to be late. And the idea, the business idea behind it was more to save these poor Connex passengers and not to make them go faster than they know already that when they are late.
So since you are using Rapidminer and also some other tools, how do you keep track of all the knowledge that you created over the time of 2 or more years?
What do you mean by knowledge? By knowledge, you mean the business knowledge and how to...
Your developers are creating, and the insights you're creating, special models you build up. How do you keep track of them and can reuse them in your standard?
Not in a perfect way, I would say.
May add one point. I mean, you're working at Industry Solutions, and Industry Solutions also has a Lufthansa Cargo and other branches. How do you communicate with your colleagues?
To be honest, we are just starting to do this communication and to build up a Rapidminer group of people because we are still in the exploration part in the company and we still are the nerds that like do weird stuff. But the first step was to build some kind of a template, and now we see how to make it more and more abstract so that we have this really as a template to use every time we create a new project so that we don't waste too much time. This is one part. This is the technical knowledge. And the other knowledge, like what data should we put in, what is good data, what is bad data, is just, we don't share it. So we have some meetings in Lufthansa Industry Solutions where we exchange this kind of knowledge, but only on a very rough level. And the detailed description is basically a wiki at the moment. Oh, yeah.
You learned in that example about the furnace that circumstances change over time.
Yeah.
Does that happen to your models? And if that does, when you've gone and done consultation with VW or whoever, how do they then, after you've finished your work, update their model to keep it up to date with changing circumstances?
So by using Rapidminer, we have, I think that there are actually two questions, like how do we deal with this changing environment, and what do we do in order for the models to cope with this challenge, right? Yeah. So changing environments could happen in the data, and if it happens in the data, you need to include it into the model, right? For example, seasonality. In summer, airspace is more crowded and flights take longer. So you put in some kind of a feature. And also this lagged feature, so increase the probability for guessing the right number in here. If it's a change in data that is not built into the model in some way, then there's no hope to do that, because you need someone to look at the model and to incorporate this new change into the model. And I don't think that there's any way to get around that except for reopening the project. So for example, if Frankfurt Airport decides to turn around its infrastructure completely, then you will need to build new models, right? If the change in the data is so severe that the model cannot at all incorporate it, then yes. But this is a general pattern, so that's nothing specific to our company or so. The second thing is that we build processes using Rapidminer where we check the performance automatically of the models. And for example, there are some standard approaches like when the performance of the model goes below a certain value, then retrain the model, or retrain the model just every week. So if the situation doesn't change too severely, then we're not needed afterwards because the model retraining is automatic.
What would you recommend to companies starting their own data science team now, for example? What kind of governance or funding model should they go after? I mean, not every company has the luxury to have a whole legal unit where you can do some intra-company billing, I guess, or I guess your customers have to pay for your service.
So the question was what a good funding model would be in order to start a data science group inside the company. Yeah. As I'm really the technical guy, the computer guy, I'm not that much into the legal details. But I'd say, as a recommendation, we can offer some help and service to you, of course. For a really cheap price, we will help you set up this data science group without having the need to hire people for many years.
I think there's a general question whether to have a centralized data science department at one location, or like you work with your colleagues decentralized in various branches. Would you say one is better than the other, or you need to have a mixture, or what would you prefer as a data scientist and not as a, how you call it, business guy?
So for me, as a data scientist, it's only important to have some exchange with other people in order to gain some knowledge from their experience and to share my knowledge with them. So whether or not we work decentralized is not so important to me.
But no basement.
Yeah, well, yeah.
Okay.
Probably that means that I don't have any basement.
Further questions?
Who's finding the business cases for you? I mean, this what you show is pretty
Yeah.
straightforward thing. Who's finding them for you?
It's a good question. So the question was who's making up the business use cases for us. We, in particular, are in the Lufthansa group, the people that I work closely with, we are data scientists. So we don't have that business knowledge. So we cannot really cook up some new business cases. And so for that reason, we work together with different digitalization strategy programs in the Lufthansa group. One of them is called Obsession, which also pays some data scientists from time to time. And they come up with some use cases and they see what processes and how the processes could be improved using predictive analytics, and then they approach us and say, hey, we need 2 data scientists or 3 data scientists in order to realize this and that project. Can you do it? And then we say, okay, we get the data. Yes, we can. We say.
If you compare this with pricing, so is this a much more difficult modeling process, or because pricing can be very complex?
You can screw up every model or modeling process so that it becomes really complex. I don't think that they are someone here asking me to compare apples to bananas. So one is an apple, one is a banana, and it depends on the data and on the complicatedness of the processes that lie around the process that you want to improve, right? How it interacts with the rest. At the Lufthansa group, I think we have some predictive models in there as well. I'm not so certain though, because this is not we are in operations, meaning that we work with predictive cases considering aircrafts and the movement of aircrafts and the operation, the handling of aircrafts. And there's another project called SMILE in the Lufthansa group, and they exclusively deal with the passenger stuff.
Using Rapidminer?
Using partially Rapidminer, yes.